right? So as discussed earlier, I will be, yes, I will be solving and discussing class tests for 2018 and 19, so that can have uh, you guys can have good preparation uh, for the upcoming test on Tuesday. You guys can see my screen, right? No problem. Good. All right. That's cool. Okay. So let's start. So basically, if you can see the first question, if you can open up the PDFs, download, and if you can see the first question is it discusses that, okay, if you see this problem, it says that you have a line charge, right? With it's infinitely long and its density is lambda, and it's positively charged. And also you have another positively charged on a positive charge that's suspended above this positively charged line charge, right? So basically, suspending means that this positively charged Q, it's floating, right? So that means net force on this charge is zero, right? Now, of course, this one, if they say like what is the sign of the charges on the wire, right? So I mean, if you see they said like it's suspended. If you read the question, it says it's suspended. So that means it has to be positive. So basically, they are just trying to see if you can understand that it's a repulsive force acting on the positive force. Because if it was, let's say, the line charge was negative, then you would have faced an attractive force downwards, right? But since it's suspending, that means there is a force acting outwards or upwards. So there is a force acting upwards onto this charge. So for example, if you have a positive charge Q, and since if for and this one, for example, you have a gravitational force, right? So now to suspend this force, you have to cancel out this gravitational force. So you need another force upwards acting, right? And then this could be your electrical force, right? This E is basically the E field that has to be produced by this line charge, right? And this Q is basically this Q. So now, therefore, you should have an upward Coulombic force to balance out this downward gravitational force. So basically, for this one, you need FQ equal to FG, right? And since you need an upward force, therefore, you know that the electric uh, field has to go upwards, right? And since the electric field has to go upwards, it's repulsive, it has to be positively charged. So that's your justification. So draw some diagrams, draw some equations so that we understand that you know it clearly what's going on. All right. So now they said like, okay, you have to find an expression for the line charge density, right? In terms of Q, M, and lambda. All right, people are still trying to join. That's good. All right. And so you have to find the line charge density, lambda, right? You have to find this in terms of the mass of the charged particle and the Q, charge of the charged particle, right? So we know that for to suspend the charged particle, you have to balance the electrical and the gravitational forces, right? And the gravitational force is basically mg. This is the gravitational constant. And since this is a line charge, right? So for a line charge, what's the electric field for a line charge? We have derived that in the class. That's like if you have a line charge density of lambda, that's like 2 pi epsilon naught r, right? R is basically the distance from the line, right? So in order for this force to balance, you need Fq to be equal to Fg. So basically, this Fq is basically Q into E, right? So I mean, this electric field is the electric field of this line charge, right? So now, if you have all these values, you can find lambda, which should be equal to your mg, right, times 2 pi epsilon naught r divided by q, right? So basically, that's what they're asking from you in this. part B, that find the line charge density if in terms of the amount of charge and the mass and other parameters. The other parameters are distance. What's the distance between the charge particle and the line charge density, right? So that's the answer for your part B, right? And that's for part A, including the diagram. All right. So any question till now? If there is no confusion, okay, I'll then proceed. This is pretty straightforward, honestly. Now, if you see the part C, right, it shows that now in addition to this basic, so initially you had the positive line charge density, right? So this is the positive one. We already did this in part A, and now additionally you have a sheet of positive charge. So this is a line charge, which has a line charge density of lambda. This is a sheet of charge density of sigma, right? And now remember, this Q is suspended, right? Initially it was suspended, so the net force was 0. So now once you put, so net force was 0, that means if you have this charge, wait, people are trying to join right now. All right. So basically when you have initially a charge Q, you balanced out the gravitational force with the electrical force, right? So therefore your downward upward forces are balanced, and there were no left right forces, right? So basically all the forces were 0, all from all the sides they were 0, right? But right now additionally you are placing a sheet of charge to the left of this positive charge, and it's also positive, right? So you know that the downward force is balanced by the upward electrical force. That we did in part B, right? So now the only force that's been projected by the sheet of charge is the repulsive force, but that's horizontally, right? Because it cannot come at an angle right now because it's placed just vertically with the charge. So therefore, and since it has to be a repulsive force, the force has to go to the left side because there is no other force coming from it, right? And we know that the electric field from a sheet of charge, it's homogeneous, it's fixed, it does not vary with distance, unlike the line charge, which varies with distance. And what's the electrical field for the sheet of charge? Can anybody tell me? All right. So basically, for the part, okay, so people are trying to join. Okay. All right. So for part C, it basically says that what direction the charge begins to move, right? So the charge begins to move to the left, right? Because the downward force is balanced. It cannot move up and down. It's already balanced from part A and B. So it has to move to the left, right? And now what you have to do is, like for part D, you have to find the velocity by which the charge moves, right? So once you place the sheet of charge, this Q starts to move to the left. So you have to find the velocity with which the Q moves to the left, right? So now we know the electrical force to the left, right? The electrical force acting, the left electrical force acting to the charge is basically QE, right? And this E is basically the electric field of the sheet of charge, right? And we know the sheet, for the sheet of charge, the electric field is sigma by 2 epsilon naught. Can anybody tell me why the 2 is coming here? Anyone? The reason for the 2?
It's because the electric field lines will go on both the sides of the surface.
Exactly, yeah, exactly, yeah. So it's going from both the side of the charge surfaces, right? But you are considering only one side because we are only considering the effect on the charges, not all sides, but nonetheless you have to take the 2, right? So this is the electric force that's acting on the particle. Now when there is a force, like when there is a force like this one, there's an electric field because of the sheet of charge. It forces the Q to the left. Now when there's a force, there's an acceleration, right? And we know that force is related to the acceleration by F is equal to ma. That's the Newtonian law, right? And the acceleration is basically nothing but dv by dt. That's the rate of change of the velocity with respect to time, right? For example, like if you have a velocity curve, let's say if you have a velocity curve like this, right? So that means this basically tells you the gradient of, or the rate of change, right? So basically, since for the starting region, let's say for region 1, this gradient is flat, that's horizontal, so the gradient is 0, so your acceleration is 0. So basically the dv by dt of the v time velocity times velocity versus time graph gives you the acceleration. So the acceleration of this part is 0 for the first part, right? So for the second part, you see there's a downward slope, right? So since there's a downward slope, the acceleration has to be negative, right? Because that's the gradient. dv by dt is gradient, it's negative. Similarly, for the third part, it's 0 again because that's horizontal. For the fourth part, you have a positive slope going upwards, so the acceleration has to be positive, right? So this is how acceleration is related to your velocity, because you have to remember the velocity. So you have to go like that. Since you need the velocity, you need the acceleration, because you have to connect this. To find the velocity, you have to connect it with the initial force on the left, right? So that's why we start with the force to the left. We find it, then we connect it to the Newtonian equation. Then we'll plug that, okay, since we know acceleration is equal to dv by dt, so therefore your this force, basically m, the Newtonian mechanical force, has to be equal to the electrical force, right? Has to be equal to this electrical force, QE, right? So since we know acceleration is dv by dt, and this one we know it's sigma by 2 epsilon naught, right? So now what we could do is that we could do, since we need v, right? So we can keep dv on the one side and just put dt on the other side, right? You can put dt on the other side. So now if you want to do the integral, right? If you want to do the integral to remove this dv, since this is dv, so you have to do the integral on both sides, this one in terms of dv, and on the right hand side in terms of dt. All right. So for this one basically becomes mv, right? Because if you take the integral 0 to v, you have a variable v. You plug in the values, it has to be mv. And this one becomes sigma by 2 epsilon naught qt, right? Because you just have another variable. So this is basically, so okay, so this is basically q sigma 2 epsilon naught t. This is basically saying that, okay, if you have, let's say, y equal to m, now if you integrate it in terms of x, let's say if you integrate it in terms of x, if I integrate everything in terms of x, let's say, right? Okay, not on one side, okay, let's say both sides, so that becomes like mx, right? So that's the other way of saying this one. So this is what we are doing here. We are just integrating left and right. And since the left integration is v, you will end up having v, the velocity that you need, and on the right it's t. So now just replacing the values, you will have q sigma by 2 epsilon naught divided by m, right? So that's the equation that they are looking for in part D. All right, so it's just finding. So basically when you place this sheet of charge, it will apply a force on the left, which will apply an acceleration, which will cause the charge to move with a velocity that you can find from the Newtonian equations. All right. Any questions regarding this? All right. I hope, yeah, because since I'm working in the other window, so it would be better if you guys speak up if you have any questions. Yeah. All right. So let's proceed on question 2 then. All right. So for the question 2, it says that initially your C1, you have two capacitors here, right? Two capacitors. This one is 8 microfarad, right? This one is 8 microfarad, and your C2 is 4 microfarad. So now initially this C1 was charged and placed in the circuit and is charged with a voltage of 120 volts, right? And this one was uncharged. So this C1 is charged and this C2 is uncharged initially. So now once you connect the switch, let's say you connect the switch, so this C1 and C2 will be connected, right? So we will end up having a circuit something like this, right? So now these two are connected, right? So initially, when let's say the switch was not connected, let's say when the switch was not connected, initially for the C1, for the 8 microfarad, I had a potential of 120 volts. So since you have a potential, so that means you have a charge stored inside it, right? So then they said, once you close the switch, what will be the potential difference across each capacitor, right? And the charge on each capacitor. So after you close the switch, what happens? Like how is the charge distributed? Because initially only this one is charged. But once you close, both will be charged. So how much charge each one is having and what's the potential difference, right? So initially, so the total charge in the circuit is being stored by C1, right? And since you know the capacitance, which is 8 microfarad, and you know the potential, so you know how much charge is stored by this capacitor C1, right? So which is equal to 8 microfarad times 120 volts, right? So this is the amount of charge initially stored by the by the by C1, and which approximately equals to, let's say, 960 microcoulomb, right? So now when you connect the switch, some charges will move, right? It will move to this capacitor. So the potential has to drop. It will no longer be 120, it will drop. It will drop until the potential across both the capacitors are equal, right? Remember, this one is 4 microfarad, right? This capacitance is more 4 microfarad, so this will charge faster than the discharging of the 8 microfarad, right? Because that's storing more charge. Now, since both these capacitors are connected and they are connected in parallel, remember, because these two junctions are connected with a short circuit in between, and these two capacitor junctions are connected by a short circuit. So now the complete capacitance, let's say, the total capacitance after you connect the switch has to be, since it's parallel, it has to be C1 plus C2, right? Because capacitances in parallel, they add up, right? So therefore the net total capacitance of the circuit now is 12 microfarad, right? So now you have 12 microfarad to store this amount of charge. That's the total amount of charge that's in the circuit, which was inside C1. So therefore, since you increase the capacitances of the entire circuit, so therefore the potential has to drop, right? So the V1 has to drop from 120, right? So you apply the same equation here. So basically Q equal to CV, but this time your Q is 960 microcoulomb and your C is 12 microfarad. So now your V is basically, just divide that up, V is basically 80 volts. So basically the potential dropped from 120 volts from C1 to 80 volts, right? And it makes sense because some charge has moved. So the potential across C1 has to drop, but it will drop until the until the potential on both the capacitors are same. But it doesn't mean the charges on both the capacitors are same because their capacitance are different, right? So therefore, now what's the new amount of charge stored inside C1 and C2, right? So since the potential has become 80 volts for C1, your Q would be, total amount of charge is basically 8 microfarad times 80, right? So that's like 640 microcoulomb, right? So you see, they need the charge drop, right? And how much charge drop is the same amount of charge that has been stored into C2, right? So that has to be equal to 320 microcoulomb. So the total charge is conserved, if you see. The total charge is conserved, 960. What happened is just once you connect the switch, some charge moved from C1 to C2, decreasing the potential drop across C1. So that's your part A. Right. So in part B, what they asked is that you have a parallel plate capacitor, right? So you have a parallel plate capacitor and you have the capacitance, right? This is the initial capacitance, 5 nanofarads, right? And you had a potential across this as 120 volts. Now you immersed it into water. So initially consider you had air inside, right, as the dielectric. But now you have water, right? You immersed this into water. So once you immerse this into water, and the dielectric constant of water is 80, so what happens? You have water all around, right? So you have water all around. So now water will be filled inside the capacitor, right? So now water has a higher dielectric constant than air, right? So since water has been filled inside, so the capacitances, right, will change. And now what happens? Like since it's a dielectric, it can store more charges. So therefore the capacitance will increase, right? So once the capacitor increases, the voltage across the capacitor has to decrease, right? So the capacitance. So initially you started with 5 nanofarads, but that was for air. Let's say that was for air. But since now you have water inside it, because you immerse the capacitor into water, your new capacitance will be K times this 5 nanofarad, right? So that's like 400 nanofarad. So you see the capacitance increased. The capacitance increased, right? So since the capacitance increased and the total amount of charge is same, right? Because the charges are not changing, right? Same as before. Your Q is same for both the cases. Your Q is same. So now if Q is same, but the C increases, therefore the V has to decrease, right? So therefore, since V is equal to Q by C and your C increased because now you have water, therefore the V has to decrease, right? So the V decreases by the same amount as C increases. So the new V is 120 by 80, which is equal to 1.5 volts. Yeah, which is equal to 1.5 volts. So you see, in air, a capacitance of 5 nanofarad could hold an amount of charge with 120 volts across it. The same amount of charge can be held if you keep water in between the plates with a smaller voltage, with only 1.5 volts. Because now you have more capacitance. So build 1 volt, you need more charges to store. That's what it means. Because a dielectric has a higher capacitance. So for 1 volt increase, you need more charges, right? So that's what happens. Like now, since Q is fixed and the capacitor increases, therefore the voltage across the terminal decreases. So it's a huge decrease if you see by a factor of 80, right? So that's why in capacitances, you prefer high dielectric constant materials because then you can store a lot of charges. That's like in batteries and other stuff. All right. So now, okay. So for part C, if you look into part C, any question for part B? Any confusion regarding part B? Okay. Why are they in parallel, not series? Okay. Because like for series, right? For series, okay. Now remember, if there is a short circuit or if it's connected by a wire, so that's like the same potential on the same node. Let's just consider that, okay, let's say if you have a capacitor, right? Let's just say one terminal as node A and the other terminal as node B. All right. So now for this capacitor to be parallel with another capacitor, let's say this is C1, you need both the nodes to be connected directly, right? So therefore, if I short circuit, if I connect this by a wire, so ideally a short circuit has a voltage drop of 0 because it has no resistance. Ideally, a short circuit has no resistance, right? So if I say if I have V1 at this point of voltage, I would have V1 at this same point because there is no drop across it. Similarly, if I have V2, I will have V2 across it. So now my C2, I can say it also has node A and node B, let's say. So these two nodes are equal. Now I can say they are in parallel, right? But what happens in a series, let's say, let's consider this one, right? Now you see, I have one node, but there is a capacitance. So definitely the voltage of VA is not equal to VB, right? Similarly, for node C, the voltage is different than voltage B, which is already different than voltage A. So my voltage A and voltage C are not equal. So therefore, it has to be in series, right? It has to be in series in this case. Now, to make it parallel, you just have to connect A by C with a short circuit. Then it will become parallel. Otherwise, it is not. Right? And in parallel, remember, if let's say if there is a current going, let's say if there was a current going I1, in parallel, the current would divide into two branches, right? Here in this case, up and down. So in parallel circuit, the current divides up, right? But in series, whatever current is going through A is the same current going through B, is the same current going through C. There is no division, right? So this is the difference between the parallel and the series circuits, right? All right. All right, no problem. Yeah, okay. All right. So now for part C, any volunteers for part C? You have three current conductors, right? Case A, look into case A. Okay. I need to maybe I can squeeze this here, maybe. Yeah, hopefully. Yeah. So look into part A. You have a circular cylindrical wire, length A, length L, radius A, conductivity sigma naught. Case B, you have a block, length A with square side length. That means it's AA, so area is A squared, with a conductivity of double than that of the case A. And for case C, you have something changing, right? You have a changing wire with a changing radius. The minimum radius is A because the start and end radius is given as A, right? In the middle, the thicker one, you have radius of 2A, so that's like double. And the conductivity is same as case A. So case A and case C conductivity is same, right? So now what you have to find is that they say the same amount of current is flowing, right? So you have the same amount of current flowing through all the cases. So through this one, you have I naught. Through this one, you have I naught. Through this one, you have I naught. So in terms of current, it's the same, but the areas are different. The conductivities are different. So now what they ask is circle either true or false for each of the following statement. The largest current density is found in case C. So now, is it true? Is the current density? What's the current density? Current density is J, right? Now the current density is J, right? The current density is basically I by area, right? So that's the area through which this current is flowing. And remember, the current flowing is same. So I is same. What matters is the area that's changing, right? So now you have to say, is the largest current density flowing through C? Is it true or false? Anyone? Any volunteers?
False.
All right. Anybody else? All right. So anybody wants to counter this, or is it true? All right. So yeah, that's false, right? That's false because if you want for case, if you like, for example, for case A, right, case B and case C. So now what you need is that area, right? So the area, this area for case A is pi r squared, right? So A is basically pi r squared, right? Or pi a squared, let's say, because the radius is A. For case B, since it's a square, the area is a squared, right? Length into width, the area, right? Now for case C, if you see, the area is changing. Now, what you want is the current density. So now what you want is the maximum of the current density, right? So what you could do is you could work with the minimum area. I mean, you could take this area of the thicker region, but what you need is that the largest current density. So for the largest current density, the area has to be smaller, right? So why don't you take this smaller area, which is equal to also a square, right? So now, if you see, if the same current is flowing through all the cases, right? So for the current density for case A has to be pi a squared, and for B, a squared, I by a squared, and for C, it also has to be, all right, sorry, for case C, yeah, since it's a circular region, it has to be pi a squared. Yeah, so for case C, it's also pi a squared, right? So clearly you see the area of the B is smaller, so the current density has to be larger for case B. Therefore, this is false, right? Okay. Now the resistance for case A is larger than that of case B, right? So for case A, we know the area. For case B, we know the area. So now what's the resistance, right? Resistance is basically rho L by area, right? A. And what's the rho? Rho is basically 1 by sigma, right? The conductivity. The conductivities are given, right? The conductivities are given for all the cases. So now for A, it's L by sigma A, which is equal to your pi a squared, right? For B, it's L by 2 sigma A squared, right? So clearly, you see you have L by sigma A squared in all, but this is divided by 2 and this is divided by pi, and pi is 3.14. So therefore, definitely pi is greater than 2. Therefore, the resistance of case A is smaller than case B. Therefore, this is also false. All right. Okay. If there is no question, then maybe I'll move to question 3. All right. So in this part, if you see, what you have is basically you have a beam of electrons, right? So you have a beam of electrons. So that means what you have is a charged particle, negative charge particle, right? Is traveling with a velocity v through a magnetic field that's going into the page, right? So now, what's the direction path of the taken by the electron? So now, if you apply the right hand rule, right? If you apply the right hand rule, you know that the velocity, since it's an electron, this is the beam of electron moving like this one. But what you need is the direction of the current. So the direction of the current is opposite, right? Because since it's electron, the direction of the current is opposite. And now when you apply the right hand rule, you will see that if for an electron moving like this, the current is downwards, right? I, and you have magnetic field like this. So when you apply the right hand rule, you will have a force acting to the right, right? So clearly B cannot be the case, C cannot be the case. It has to be either A and D. Now once you have a right force, angle force, the angle of the force changes, right? You see the angle of the force changes. So therefore, it continues, but it takes a curl direction. For this one, it just shows that it moves to the right for part D, which cannot be right, because at this point you have a force in this direction. At this point you have a force in this direction. At this point, you have a force in this direction. So it has to move down, but it doesn't move down. So therefore, D has to be wrong. So therefore, A is your correct answer. Right. So since they just asked, circle the correct answer, right? In this case, you just have to circle. But if they say justify, then draw some diagram visually to show that you understand what's going on, mainly the right hand rule. Right. All right. So now for part B, if you see for part B, what you have is a circular loop, right? The radius is given and the current flowing is basically 10 milliampere. And notice the direction of the current flow, right? So you have 10 milliampere flowing through this loop, and the current through the straight line is also given, which is equal to 25 milliampere, right? Now you have a loop current and you have a straight current, right? So now since you have currents, you would have a magnetic field, right? So now the magnetic field, you can use it to find the direction of the magnetic field. You can use the right hand grip rule. So the thumb points to the direction of the current and the curl of the fingers tells you the direction of the magnetic fields, right? So if the magnetic fields, because of this I2 is coming out of the page, right? If you curl your fingers, it comes out of the page. Now, the direction of the magnetic field for this circular current is going into the page, right? If you apply, it goes into the page. Now, at this center, you have magnetic field going into the page because of this 10 milliampere, and you have magnetic field coming out of the page because of this 25 milliampere. But do remember that the magnetic field, the intensity of the magnetic field, right? If I say this is B, it falls with distance, right? It falls with distance, right? For both the cases, it falls with, it has a distance dependence. It's not fixed, right? So therefore, the first question tells you what is the magnitude and direction of the magnetic field at the center of the loop. So at the center, you have two magnetic fields working, one because of 10 milliampere, the other one because of the 25 milliampere, right? So basically, for the loop of current, the direction is into the page, right? And the magnitude for the loop of current, as discussed in the class, is given by, like for example, I can write this as I, right? Which is equal to my 10 milliampere divided by 2R, right? And R is the radius in this case, is the distance from the loop current, right? Which is equal to 1 centimeter. Now do convert this into meter once you plug in the values. All right. Okay. So in this case is the capital R. So this is the magnetic field intensity for the loop. For the line current, we know it's mu. In this case, it's I1. Okay. For the line current, it's I2 divided by 2 pi. In this case, is D, because D is the distance from this line current to the center, right? Which is equal to 2 centimeter. Convert this into meter. All right. So now we have B loop and B line, right? So now this one is directed downwards. This one is directed upwards. Sorry. Yeah, this one is directed upwards, right? So clearly these magnetic fields will be interacting, and it will be trying to counteract each other, right? So basically your B total has to be the difference between this one, right? Has to be the difference between this one. So if you take this direction as the positive direction, let's say, and this one as the negative direction, then basically what you have is B loop by B line, right? So this is the total magnitude that you have. Once you plug in the values, you'll find the magnitude and the directions. So basically, once you plug in the values, right, what you will get is that for B loop, that's like 2 pi into 10 power minus 7 Tesla. And for the B line, it's 2.5 into 10 power minus 7 Tesla. Oops, minus 7 Tesla. Right. So clearly this is a positive value, right? Because 2 pi is something around 6. So clearly this is a positive value. So therefore your B total at the center, is a positive value of, let's say, something like 3.78 into 10 power minus 7 Tesla. And since you defined positive as going into the page, therefore the net direction is into the page, since this is positive value. So just define according to your convention and then write your answers according to your convention, right? Because maybe somebody defines going into the page as negative, right? So therefore your value will be negative. But it doesn't matter once you define the directions. All right. So for part B2, it says what value and direction of I2 would produce zero magnetic field at the center. So since you know that the two magnetic fields are counteracting, there is a possibility that and since you know that the currents are not same and the distance are not same, right? Because the distance of the center for loop of current is R and the distance from the wire is double that, right? So the D is 2 centimeter and R is 1 centimeter. So therefore, there is a chance that if you can change I2, you can basically make this B total to be 0, right? But for that, what's the value of I2 that is required? So that means I1 is fixed, right? So therefore, for B to be 0, you need your B loop, which is going into the page, or which is the positive direction that you took, has to be equal to the B wire or B line, right? B line of current, which is directed out of the page and which you defined as the negative, right? So what you need to do is just you have to make mu I1 by 2R equal to mu I2 by 2 pi d. Right, so therefore the mu's will cancel, the 2's will cancel, and what you will have is basically I2 equal to I1 by R into pi d. So since you know all these values, you can plug in the values, and then you can get a value for I2, which is equal to 62.8 milliampere. All right. Okay. So now, yeah. So now, okay. Yep. All right. So now if you consider part C, it tells you that you have two conducting wires, right? One is this one, and the other one is this one, external. Two cylindrical conductor, inner conductor radius of 1 centimeter. Convert those all this into meter because everything is given into centimeters. The inner radius, for the external conductor, the inner radius is 3 centimeter and the external radius is 4 centimeter, right? So therefore, so you know the thickness is just 1 centimeter. So now the conductor carries, let's say, current. The inner conductor carries a current of, let's say, 40 milliampere, right? Similarly, the same current is being carried by the external conductor, right? So now they say that, okay, the first verse tells you what is the magnitude of the magnetic field at radius r equal to 2 centimeter. That's like between the inner and outer conductors, right? So since you know the B is 3 centimeters, so what they are asking is basically they are asking you to find the magnetic field that's between the two conductors, right? So let's say this is a conductor, they're asking you to find the magnetic field at this region, right? So now how do you do it? You can apply the Ampere's law, right? So why don't you apply the Ampere's law to find the magnetic field, right? So why don't you take this line into two, right? So since you know there is a current flowing, I equal to, let's say, 40 milliampere. So now let's define the direction. Let's say for the internal one, the direction going on the right is positive and the direction coming to the left is negative. Let's just define. So that means I have minus 40 milliampere outside externally and plus 40 milliampere inside, right? So now what Ampere's law says that when you do the line integral, it has to consider only the current that's enclosed by this line integral, right? Nothing outside. That means you only consider the internal current. This one is not of your concern right now, right? So when you do the closed line integral, let's say dl, right? So that has to be mu naught I, right? So now this I is the internal I, right? Plus 40 milliampere. That's the current that's going in the internal conductor, right? And this one with a radius of 2, you know this radius, with a radius of 2, right? So what's the line integral for this circle? This is a circle, right? So this region is a circle. This one is a circle with a radius of 2, right? So the line integral for this one has to be 2 pi r, right? Since it's a circle, r being 2 centimeter, and this I is basically 40 milliampere, right? So when you plug in R equal to 2 centimeter, convert them into meter, this one as 40 milliampere, what you get is you get a magnetic field intensity of 4 into 10 power minus 7 Tesla, right? That's what you get. So you have to do Ampere's law to get the equation, which is pretty straightforward. Plug in the values. The main thing to consider here is like, which currents do you take? Do you take all or do you take one? That's what they're trying to test it here. So you just have to take the current enclosed by the line integrals. So that's your first part gone, right? For the second part, they say what's the value of B at a radius of 5 centimeter. Now your C is 4 centimeter. So that means you are looking for an area that's enclosing the entire thing, right? That's enclosing the entire thing. So the net current, so if you apply Ampere's law, right? If you apply Ampere's law, let's make this vector. It basically tells you how much current is enclosed, right? This one is the enclosed current. So in this case, this is what? 40 milliampere positive minus 40 milliampere, right? Because you are enclosing both the currents, the internal and the external, both. So therefore, your enclosed current is basically 0 milliampere, right? So since this is 0, your net magnetic field is basically 0. You don't have to go calculate for that.